Hi everybody, welcome back. In this video, I'm going to give you an introduction to chemical kinetics. So let's get started. Thermal energy produces constant molecular motion, causing those molecules to collide with one another. So we're going to talk a lot about collisions in these series of lectures on kinetics. So what's colliding here? So we're always thinking about electrons. Electrons are where the chemistry happens. So electrons in one molecule are attracted to the nuclei of another molecule. I've said before in previous videos of mine that one of the overarching themes of chemistry is that opposites are attracted to one another. And when this happens, bonds are broken and new bonds are formed. And that's where we have a chemical reaction. I abbreviate reaction as RXN. Okay? So let me repeat that again. So thermal energy, right, gets those molecules really excited. I like to think of them like dancing molecules. They're in constant molecular motion. And always thinking about what's in my beaker. Well, these molecules with enough thermal energy begin to collide with one another. And electrons are where the chemistry happens here. So electrons in one molecule are attracted to the nuclei. And remember, the nucleus is a positive charge. So the nuclei of another molecule, opposites are attracted. When this happens, bonds are broken, new bonds are formed, and a chemical reaction occurs. Okay? And if you go on to take organic chemistry, you will learn a whole plethora of chemical reactions where you have to break bonds and form new bonds. Okay? But it's not the point of this chapter. In this chapter, we're going to talk about reaction rates, how fast reaction will occur. So why do we care, though? Well, a product cannot form if the rate at which it forms is just too slow. So later on, I will have a series of videos on thermodynamics, and we'll talk about spontaneous versus non-spontaneous. A non-spontaneous reaction will not occur. A spontaneous reaction will occur, but we also have to think about the timing, right? Sometimes reactions are just too slow, regardless if they're spontaneous or not. So if we have a knowledge of the reaction rates, which is going to be the point of this chapter. If we have a knowledge of the reaction rates, then we can make changes in our synthesis to improve the likelihood of it occurring. Then we can make changes in our synthesis to improve the likelihood of it occurring. So the study of kinetics will allow us to really understand reactions at the mechanistic level. If we know the mechanism of the reaction, which I'll discuss in a later video, then we can make changes to the conditions that we're running a reaction in order to improve the likelihood of it occurring, like optimize it. Okay. And the human body actually has the ability to increase the rate of reaction in biochemical pathways, which maybe some of you have studied in your biology classes. through the use of enzymes, which are globular proteins. And I'll touch base on this at one of my later lectures when I discuss catalysis. All right, so let's talk about the collision model. For a chemical reaction to occur, collisions between atoms, molecules, and ions must happen. I mean, that's just no chemical reaction is going to occur if these particles do not collide, right? So that's just the premise of the collision model there in a nutshell. So let's look at a reaction here and discuss what factors do affect a reaction to occur. What kind of changes could we make? So we have reactants AA plus B to make product AB and then A, right? So this is the reaction we're running. Just so you know, I will abbreviate concentration of reactants as such. So anytime you see brackets, that usually indicates concentration and molarity. R is standing for reactants. So concentration of reactants and molarity. Remember, molarity is moles of solute over liters of solution. All right, so let's think about what could affect this reaction. How can we increase the number of collisions, right? We want things to collide. Well, one thing that you can change is the concentration. As you increase the concentration of the reactants, think about your beaker. If we have more of these guys in our beaker, right, it's inevitable. It's getting crowded in there, right? We're adding more and more. They're going to collide, right? So we increase the number of collisions, which based on collision theory, helps to increase the reaction rate. More collisions means more bonds are broken and more bonds are formed, right? What's another factor do you think you could change in order to help increase the reaction rate? Good. So some of you may have said temperature. And definitely when you're in the laboratory, temperature is something we use all the time. So for example, when I would run my polymerizations and I would make polystyrene, I would run those polymerizations at 300 degrees Celsius using an oil bath, right? Temperature was my best friend in order to get longer chains. So as we increase the temperature, think of the molecules in your beaker. They start to get more of that thermal energy. They're moving around, they're dancing around. It's inevitable that they will experience more collisions, and therefore more collisions leads to a higher reaction rate. And then there's a third factor, something you may not have thought of, but we will investigate a little bit more right now. And then if you go on to take organic chemistry, you'll definitely discuss this in greater detail. And that is the structure and orientation of the colliding particles, of those reactants. So for example, let's compare two reactions. We have reaction 1 and reaction 2. Reaction 1 is what we just looked at here, where reactant AA plus B, this bond breaks and we make a new product AB, and then A is right there as like a byproduct. And what we'll notice is that B can attack from either side. It doesn't really matter here. So B can attack So it can attack from this side here, or it can attack from this side. Either way, it's going to make the product AB. But let's say we have a reaction where we have AX plus B gives us AB plus X. Now B is limited, right? B needs to attack from a specific side and then kick X out. It's like, get out of here. We'd call that the leaving group, by the way. It would kick X out to make the product AB. And so B must attack from a specific side. So looking at reaction 1 versus reaction 2, which one do you think would have a higher reaction rate or would be faster? Yes, definitely reaction 1, because we've increased our chances of making the product by not having that limitation with orientation. Whereas for here, we have to be specific where the attack happens. So this is something you would dive into great detail in organic chemistry. For example, you would learn a reaction called SN2, which stands for nucleophilic substitution second order kinetics. So kinetics will come into play again as you go on your chemistry pathway. And so an example would be if we had chloroethane here, or ethyl chloride, and we were reacting with hydroxide. So hydroxide, you would learn, is a great nucleophile, and it would attack this carbon and kick off this chlorine, but it would have to attack from a specific side in order to kick that chlorine off as our leaving group. So you would get ethanol and then chloride as our leaving group. So we always say SN2 does backside attack. It's very specific in the way that it's going to react. And if there's anything too bulky nearby, it does slow down the reaction rate or prevents it from occurring. And so you will look at all those different variables here. Now, some of you may be looking at my work and saying, well, why does it attack that carbon there? Remember, opposites are attracted to each other, and chlorine is electronegative more so than carbon. It pulls the electron density closer to itself. So that carbon is partial positive. You would learn that this is a nucleophile. It's electron rich. It attacks an electrophile, which is electron poor. And then because carbon can only have 4 bonds, something has to go. And that will be the halogen here. It goes off as a halide. And actually, halogens are great leaving groups because they don't really want to share electrons. They like to be on their own. And so you would learn this chemistry of alkyl halides used in these different substitution reactions and elimination reactions. But I just wanted to give you an example so that if you see this reaction in the future, you can tie it back into kinetics. And you would study that, okay, this is second order kinetics versus SN1, which is first order kinetics. So we'll dive more into that in later videos, not specifically with organic reactions, but what it means to be first order and second order. Okay. All right, I wanted to show you a figure here that gives you a nice illustration of a reaction with a fast rate versus a reaction with a slow rate. So when we run these experiments, we always have to have a stopwatch. We have to determine this data experimentally, and this chapter will be very data forward. So I want you to feel comfortable with looking at data, analyzing it, and extrapolating out important pieces of information from it. So you can see here reactant A is in blue, B is in red, and then C is in green. And then initially, all we have is reactants, and then they start to collide, break bonds, form new bonds, and we start creating our product. And we see over time that product C is created quite quickly in comparison to X, Y, and Z. So X is in green, Y is in blue, and Z is in pink. You can see initially you should only have reactants, and then slowly we're starting to make some product But at the end, we still have a lot of reactants left, which just indicates that this reaction is slower than the reaction here. And you may have to change certain things, like maybe increase the concentration of the reactants to improve the collisions, maybe change the temperature, or maybe it's just a matter of the mechanism that you're working with here. Sometimes we have limitations, like I showed you here with SN2, where your nucleophile has to attack from a specific side, and that's just the nature of that reaction. Okay. So as I've alluded to already, this chapter is all about studying reaction rates. And what does that even mean? Well, reaction rate is defined as how fast a chemical reaction occurs. And you use rates all the time in the real world, right? For example, if you drive a car, the speed of a car, you talk about it in terms of miles per hour if you live in the US, or kilometers per hour if you live elsewhere, right? And so that's a rate, distance over time, in terms of speed of a car. I know a lot of my students are into nutrition, and so weight loss might be something you're considering, or weight gain, right? And so you might be thinking about pounds per week or pounds per month that you want to lose or gain. Now let's talk about it in terms of an actual chemical reaction. Let's say we have AA plus BB goes to CC and DD, and you see the little letters here represent the stoichiometric coefficients. It's really important, as always in chemistry, to balance your chemical reactions. Okay. If I want to determine the rate of reaction here, then I'll give you an example of A. So A is decreasing, right? As we are reacting, A is decreasing over time. So the change in concentration over the change in T, and we always divide by the stoichiometric coefficient, and I'll explain more why that is in a little bit. So to represent the rate of reaction, A is decreasing, that's where the negative comes in. The triangle always represents change, right? So final minus initial, and this represents the concentration of A over the change in time. So we will have to define our time interval when we calculate rates of reaction and reaction rates. And you will divide by the stoichiometric coefficient. So same thing for B. It is the decrease in concentration of B since a reactant. Divide by the stoichiometric concentration or stoichiometric coefficient times change in time. So the rate for a chemical reaction is always the change in concentration, usually in molarity, over the change in time. Whereas, for example, speed of car was distance over time, weight loss was pounds or mass over time. Right? So it just depends, your rates depend on the context of what you're studying. Now we could also measure the rate of reaction through the products. And so C is actually increasing over time, or at least we hope it is. But remember to divide by the stoichiometric coefficient. Same thing with the concentration of D. It's important that you can write the rate of reaction with respect to reactants as well as products. And you may ask yourself, well, why do I want to do that? Well, there may be a specific species in your reaction that you can measure by spectroscopy. And I will show you a video at the end of my own video to illustrate how that works for a kinetics experiment, since we're not in the laboratory right now. So, maybe I can only use the reactant A, and so I would utilize this specific reactant to help measure the rate of reaction. Or maybe I have a means for measuring D, right? But I don't have a means for measuring A, B, and C, right? So it really depends on your reaction, and so that's why it's important that you know how to derive the rate of reaction based on whatever species is in your reaction. And so this will be really important for you to learn how to use. I'll just highlight that right there. All right. So something I really want to emphasize here, students tend to miss this part. By convention, reaction rates, or the rate of reaction, is always reported as positive values. So let's go back to the previous page here. If I asked you for the rate of reaction or the reaction rate, and you were measuring it by means of A, you would report this as a positive value. The negative only represents the fact that A is decreasing over time because it's being consumed during the reaction process, right? And so that's all the negative represents. But the rate of reaction is always reported, or the reaction rate is always reported as a positive value. So let's say, for example, A decreases by 0.2 molar over 20 seconds. Then that's what you would say. The rate is 0.2 molar per second, and that's a positive, with the understanding that A is decreasing at that rate. Okay, we would not report it as a negative 0.2 molar per second. All right. You've noticed that I divided by the stoichiometric coefficients. That was like the little a, little b, little c, little d, right? The reason why that we do that is it helps to normalize the reaction rates so they are equal. Let's look at an actual example here. I think it'll make a little bit more sense if we look at a chemical reaction. So in this example I've written here, we have hydrogen gas reacting with iodine gas to produce hydrogen iodine gas. And you can see that this is balanced 1, 1, and 2, right? So let's express the reaction rates in terms of hydrogen gas, iodine gas, and hydrogen iodide. Okay, so the rate is equal to a negative change in concentration of hydrogen gas over delta T, a change in time. The stoichiometric coefficient is 1 here, so we don't have to write that in there. It's just assumed if it's not written. Iodine's the change in concentration. Remember, it's decreasing over change in time. And hydrogen iodide, though, is a change in the concentration of hydrogen iodide over 2 times delta T. So we had to divide by that stoichiometric coefficient. The reason why that's happening is because hydrogen iodide is being produced twice as fast as hydrogen and iodine are being consumed. And so in order for all of these values to be equal to one another, we need to divide the reaction rate in terms of hydrogen iodide by 2, since it's being produced twice as fast. You'll see that in an example down here that I will work in the bottom, where we use actual numbers for the same reaction. But let me just repeat that again so that it sinks in. When we're trying to figure out the rate of reaction for this entire reaction, we can write it in terms of hydrogen gas, iodine, and hydrogen iodide, right? Remember, rate is always, the units are molarity over time. Generally speaking, it's in seconds because we will be working with fast reactions. Sometimes it'll be days, sometimes it'll be years, but it's always per time, per unit of time. So here we are decreasing the change in concentration of hydrogen gas over a certain period of time, change in concentration of iodine over a certain period of time, but we're increasing twice as fast the change in concentration of hydrogen iodide, so we need to divide by the stoichiometric coefficient times time, okay, so that they're all equal to one another. Now you notice, like, we have change in time. It's really important that we must define the time interval. when calculating the average reaction rate. I'm going to highlight that. Talking about average reaction rate here. There's going to be an instantaneous reaction rate, which I'll discuss in a little bit. So when you're doing the average reaction rate, we must define the time interval. And the reason why that is because the reaction slows down as the reaction proceeds, right? Why is that? Let's just pause for a moment and think about, why does the reaction slow down as the reaction proceeds? And I'll give you a hint. Think about collision theory. Yes, hopefully some of you said it. There are fewer reactant particles to collide as the reaction proceeds. All right, so as the reaction proceeds, hopefully you're producing more product. There are fewer reactant particles hanging around in solution, so they're not going to collide as much. Less collisions means the reaction rate slows down. Okay, and when you see this in this graph here, that eventually it just kind of tapers off over time. Now, it's important to make note that reaction rates can be measured experimentally, and always are measured experimentally, by the way, by monitoring the concentration of one of the reactants or products. And I said that before, that's why it's important for you to be able to write reaction rates based on each species, because it really is dependent on your reaction what you can measure. And so we monitor the concentration of the reactants or products as a function of time. Remember, we always divide by unit time, usually by something called spectroscopy. And I'm going to show you a video at the very end here after we work this problem here, because I think it's really important that you understand this. Some of you may have had experience working with a spectrophotometer, and we have access to a UV visible spectrophotometer and visible spectrophotometers where we're monitoring the change in color. So if you have a species that is colorful, we can use the UV vis or visible spectrophotometers to measure the change of that color over time, which is indicating the change in the concentrations of that reactant or that product that's colorful. So that's just something we will see in the video, and I think it's very important since we're not in the laboratory together right now. And you can calculate, though, just to wrap up here, the instantaneous. So be mindful of what the problem's asking you. So you can calculate the instantaneous reaction rate at a specific point in time as well. And so we'll look at the data here to do that, to use that as an example, right? So the average reaction rate is over a time interval. The instantaneous reaction rate is at a specific point in time. So for example here, let's say we wanted to calculate the instantaneous reaction rate at time is equal to 40 seconds for this reaction here. And so at time is equal to 40 seconds, we have to think about what 40 seconds, how much did the concentration change at that point in time? And so you would have to look at this graph here and then figure out the change in concentration. And here it's given to us. And remember, if you were given a word problem, I'd have to provide the data for you so you can do these calculations, right? Because it's all done experimentally. And so it looks like here that at 40 seconds, that hydrogen gas has decreased by negative 0.28 molar. And here, hydrogen iodide over 40 seconds has increased by 0.56 molar. Remember, the hydrogen iodide increases twice as fast, so it makes sense that this number is twice as big as the number here, 0.56 over 0.282, right? So, to calculate the instantaneous reaction rate, you will utilize the reaction rates that you derived, okay? They're like little algebra equations where you're going to plug in numbers, right? We didn't, in this graph, iodine is not shown here, just for simplicity's sake, but you could also measure iodine as well as a function of time, okay? So, let's go ahead and do that. So we wanted to figure out with respect to hydrogen gas, since that's the data we have available over time. So it looks like hydrogen gas has decreased by 0.28 molar over 40 seconds. And so you'll notice here that I kept that negative. That's that negative here, and that's telling me it decreases. And I've also put a negative in here because it has decreased by negative 0.28. And so overall, that's where you're going to get a positive reaction rate. So we get a positive 0.0070 molarity per second. You can do the same thing for hydrogen iodide, since we have that data available. So hydrogen iodide, the reaction rate is equal to the change in concentration of hydrogen iodide over 2 times delta T, and that's a positive. So based on the graph, based on the data, it's 0.56 molar over 2 times 40. And we divide by 2 so that the reaction rates are all the same, and it is. It's normalized so that it's 0.0070 molarity per second. So once again, the reaction rate should be the same at a specific point in time. In this case, we were focusing on data from 40 seconds for this specific reaction here. You divide by the stoichiometric coefficient to normalize it so the rates are the same. And the rates are always reported as positive numbers, regardless if you're getting your data from a reactant concentration, which is decreasing over time, or from a product concentration, which is increasing over time. And we will dive in deeper about, calculating reaction rates. In future videos, we'll discuss rate laws and integrated rate laws. But just to sum it up here, kinetics just allows us to determine how fast a reaction proceeds, right? Even if a reaction is spontaneous, if it's a slow reaction, that will not be very useful for us. We can affect the reaction rate by changing the concentration of the reactants. Remember, more collisions, higher the reaction rate. We can change the temperature. A lot of times adding thermal energy gets the molecules moving more, giving them more collisions. Or we can investigate the structure and orientation of our colliding reactant molecules. So this whole video is just kind of laying that foundation for the future kinetics videos to come. Make sure you sit through it and kind of really think about it. This stuff can be a bit challenging when you're first learning it. I remember when I was a student, it was a bit challenging for me until I started practicing with it, talking about the theory a little bit more detail. But I always love to link what we learn in lecture to something you would do in the laboratory. So I found a video on YouTube that shows a scientist running a kinetics experiment using spectroscopy. And I'm hoping that this visual gives you an idea about how this data is collected and what it can tell us.
This is a demonstration of reaction rates. I have 3 vessels here. They're called cuvettes. Each has a dye at a certain concentration. I'm going to add an oxidizer to vessels 2 and 3. The oxidizer if it reacts with the dye, will turn it colorless. So I'm going to add my oxidizer now. That's 60 microliters. Mix contents. As you can see, the reaction is not very fast. The decolorization, if it is occurring, is too slow to notice. A catalyst can increase the rate of reaction, and I'm going to add a catalyst to this third cuvette here. So now we may be able to see a difference in the rate of reaction in the presence of the catalyst.
All right.
So by measuring how much color remains at any given time, we can mathematically calculate the rate of this reaction. So I will demonstrate that with the use of a spectrophotometer shortly. So now it should be obvious that the reaction with the catalyst has proceeded at a much greater rate. The red dye is almost completely destroyed in the presence of the catalyst. In that same amount of time, the oxidizer with no catalyst has not made any noticeable change in the color. So here I'm going to run an experiment with a spectrophotometer. This is the spectrophotometer. It's going to shine light, colored light, through the sample. If the sample is dark, much of that light will be absorbed. As the sample becomes less colored, more light will get through. So I'm going to measure the absorbance of light on my computer screen here over time as the reaction proceeds. To start the reaction, I'll use my catalyst again. And then I'll pop it in the machine and start collecting data. Mix the contents. The machine makes a beep every 2 seconds. It's collecting a data point every 2 seconds. On my screen here is the actual data being collected. This is the absorbance of light. So this is when it's darkest. It's getting less dark as the dye is being oxidized. So here's the final results. You can see the slope changes with time as the rate changes. It starts out fast and gets slower and slower. And down around here, it's just about finished. It's almost completely clear. So that's how you collect data that can be used for kinetic analysis.
All right. So hopefully you found that video helpful. He was, remember, measuring absorbance because based on Beer's law, something you may have covered in a biology class or your first semester general and chemistry class, that absorbance is equal to the molar absorptivity in epsilon of your substance. And so that's a constant for each of your molecules. In this case, he was working with the dye, times the path length of the cell. It's either represented by letter B or L, times the concentration. And what's really important here is that there's a direct relationship between absorbance and concentration. And we saw that when he added the oxidizer with the catalyst to the dye, that over time it lost its color. It was changing. A chemical reaction was occurring. And he could measure that using the UV-Vis spectrophotometer. He measured the absorbance. And from that, he can figure out what the concentration over time of that particular molecule. And in this case, it was a reactant, so it was decreasing over time. Okay, so maybe if some of you go into research or into another chemistry laboratory, you would run a similar experiment. All right. Thank you all for watching, and see you next time.